Hi everyone, and welcome again to Nettle, the go-to place to learn about business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible, and we'd also greatly appreciate if you consider supporting us as well. So please check the link in the description or click the join button below for more details. My name is Sava, and today we're investigating quite a novel yet very relevant development in portfolio management and performance evaluation, which is the Deflated Sharpe ratio, or DSR for short. It has appeared first in a paper by Bailey and Lopez de Prado in 2014 in Journal of Portfolio Management, and has gained quite notorious attention from practitioners and academics alike since, in terms of using a more robust approach to performance evaluation of strategies when you account for both non-normality of returns as well as multiple testing or data snooping or data mining. The key concept behind the deflated Sharpe ratio is that when we are testing for the significance of outperformance for a particular strategy, we need to take into account both for its return distribution, which is fat tails or the skewness, the asymmetry of the return distribution, as well as to the number of tests that we have undertaken, the number of strategies we have tested before we arrived at the optimal one. Because obviously, if you test 10 strategies, and we've got 10 imaginary strategy data here, for example, we ran some simulations, we have done some algorithms, and we've got monthly returns over a 10-year period for 10 different strategies. Well, one of these 10 strategies would be statistically significantly outperforming at 10% just by random chance alone, isn't it? Because, well, 1 out of 10 is 10%. So taking this into account, Bailey and Lopez de Prado proposed a quite ingenious transformation and a quite original statistical procedure to take this into account in a probabilistic Sharpe ratio framework. We have investigated the probabilistic Sharpe ratio before in one of the existing videos, and this is a development on top of it to take into account not only for the fat tails and skewness, but also for the fact that we've got 10 strategies and not just one. We cannot pretend that the strategy that we would like to implement is the first we have ever stumbled upon. And that is a very common occurrence in asset management and particularly in quantitative algorithmic trading. So to start things out, let's calculate the average monthly returns, volatilities, and Sharpe ratios of all 10 strategies. So for the return, we can use the geometric mean function, applying it to 1 plus the array of monthly returns and subtracting 1. We'll do it all on monthly frequency for simplicity. We can drag it across and get monthly returns for all 10 strategies. We can see a clear winner so far. Strategy 10 has got a monthly return of in excess of 1.5%, quite a bit in front of all the remaining 9. In terms of the volatility, we can use a sample standard deviation, applying it to monthly returns, and dragging it across. And finally, for the Sharpe ratio, we need to know the monthly risk-free rate. Currently, the yield on 10-year US Treasuries is exactly 4%. So to convert it to monthly frequency, we can use the similar transformation, 1 plus 4% to the power of 1 over 12, as there are 12 months in a year, minus 1, which gives us a risk-free rate of 0.33%. Our sample size that we'll need to use in further calculations is just the count of returns for any of our strategies, 120, 10 years worth of monthly data, hardly surprising. And for the Sharpe ratios, we need to subtract the risk-free rate from the return, lock in the column here, as the risk-free rate is universal across all strategies, dividing it by the strategy-specific volatility, giving us a range of our Sharpe ratios. And we can see, even the naked eye spots that strategy 10 indeed has the highest Sharpe ratio of them all, and by quite a bit. So is this strategy indeed something genuine? Can we rely on this strategy being an outperforming one, given the fact that we stumbled upon it having tested 10 different strategies beforehand? Well, to take this into account, we need to both consider the distribution of the returns, as in the probabilistic Sharpe ratio, as well as the adjustment for multiple testing. So let's tackle the probabilistic Sharpe ratio concerns surrounding skewness and kurtosis of returns first. To do that, we first have to calculate the skewness and the curtices of each and every strategy return distributions. We can see that strategy 1 has got a negatively skewed return distribution, already slightly alarming, and positive curtices. We can drag it across and see how our beloved strategy 10 performs on this regard. Not too badly. Skewness is quite close to 0, positive, meaning that there is little to no issues here, with curtices being positive. By the way, the Excel function always returns excess curtices, so you don't need to subtract 3. This is worth keeping in mind. So this excess curtices is positive, but not something too worrisome. And now we can use the common procedure for the probabilistic Sharpe ratio to retrieve the volatility of our Sharpe ratio given skewness and curtices. To do that, we first need to take the square root. In the numerator, we have got 1 minus the skewness times the estimated Sharpe ratio. This takes into account the third moment of the return distribution, basically penalizing for negative skewness and rewarding for positive skewness, which is a very common logic in portfolio management with high moments. Then we penalize for positive curtices, adding curtices plus 2 divided by 4 times the Sharpe ratio squared. And again, this formula works only if you've got the excess curtices. If you've got standard curtices without subtracting 3, this plus 2 needs to be changed to -1. Keep that in mind. And then we need to divide by the sample size minus 1. Here we've got our sample size. We'll lock it column-wise, subtract 1, closing the appropriate number of parentheses, and get the volatility of this particular Sharpe ratio estimator. And then we can drag it across and get individual volatilities for all 10 estimators of Sharpe ratios we have got. And now for our probabilistic Sharpe ratio, let's test whether the Sharpe ratio of those strategies are substantially higher than 0, a very standard and basic test to undertake when we're dealing with probabilistic Sharpe ratio. And here we need to use the standard normal distribution. Then we'll need to introduce our z-stat, which is basically our Sharpe ratio scaled by its volatility, and then put 1 for cumulative, which allows us to calculate the probability of skill, the probability that this particular strategy is market outperforming. And here we see that we've got some promising results already. These 3 strategies have got probabilistic Sharpe ratio in excess of 95%, meaning that we are beating the market, and the likelihood of it being random is 5% or lower. This has also got quite a high probabilistic Sharpe ratio, significant at 10%. But keep in mind, we've done those 10 tests at the same time, meaning that adjusting for multiple testing is a must. And to do that, we have to modify our probabilistic Sharpe ratio approach by subtracting in the numerator this particular Sharpe ratio star. In common probabilistic Sharpe ratio, in the basic version of it, that's your target Sharpe ratio. And you can use the Sharpe ratio of the market there, or 0 as we've done here. The deflated Sharpe ratio logic objectifies this particular input and retrieves it from the trials that you made before you arrived at your optimal strategy that you believe is market outperforming. So for deflated Sharpe ratio, we need to use the standard deviation of the Sharpe ratio across trials. So we are incorporating the information that we've got from all our 10 tested strategies, in this case 10. You can easily generalize it to any number of strategies. And here we've got this adjustment factor that depends on the number of strategies that we picked, n. So here, number of trials, n is 10, because we've got 10 strategies. Then we need to incorporate this number gamma here, which is the Euler-Mascheroni constant, and it's a very interesting mathematical object by its own right in itself, in particular because nobody yet knows what the exact value of the constant is due to some mathematical complications surrounding it. However, for practical implications, you can have a reasonable precision of your results by using 4 decimal places, and it has been calculated precisely for up to 4 decimal places, so you shouldn't worry about it. And it's equal to approximately 0.5772. So that's the Euler-Mascheroni constant we're using in our calculations. And then we need our variance of the Sharpe ratio across trials. So we can use sample variance formula and apply it to these Sharpe ratio estimators across all 10 strategies. And finally, we can calculate this particular synthetic Sharpe ratio target that incorporates the information throughout our multiple testing, which is equal to the square root of the variance across trials times 1 minus the Euler-Mascheroni times the normal standard inverse distribution of 1 minus 1 over the number of trials n plus Euler-Mascheroni times standard normal inverse distribution of 1 minus 1 over n times the number e, which is the exponent of 1. This is another fundamental constant of mathematics, which is approximately 2.7. You might have encountered it before. Now we close the appropriate number of parentheses and retrieve our synthetic target that is given by the deflated Sharpe ratio process of 0.12. Again, the mathematical beauty of this adjustment process is that we incorporate some fundamental constants of mathematics, such as the Euler-Mascheroni constant and the E, the Euler's constant E, for the purposes of performance evaluation, which cannot be more pleasant for myself personally. And now, back to the essence of it, we can use the standard normal distribution. And now for our z-stat calculation, we subtract from our individual strategies Sharpe, the Sharpe ratio target we've just calculated, locking the column. As it's the same across all our trials, we are doing the set of multiple tests, and this is the relevant adjustment to make. And we divide it again by the individual Sharpe ratio volatility as per the probabilistic Sharpe ratio procedure. Then we input 1 for cumulative, and we can see that the probabilistic Sharpe ratios are indeed quite substantially deflated as compared to the individual testing case. This deflation is due to the fact that we accounted for multiple testing, as we tested for 10 strategies at once. And for the strategy 10, which was the most promising, the most outperforming, our PCR, our probabilistic Sharpe ratio, has decreased from 99.5% to slightly above 90%. So it's not as market outperforming as we initially believed, and some of its outperformance is due to random chance alone. However, still, we can interpret it as being significantly market outperforming, but not at 1%, as is the case here, but only at 10%. So we have to tread lightly. And that's all there is for the application of the deflated Sharpe ratio for performance evaluation, robust to both the return distribution and multiple testing concerns. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, finance, or economics you'd like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.